All right, so the last section of our Unit 7 is going to be approximation applications. So this can include LRAM, RRAM, MRAM, and Trapezoid Rule. Okay, so you might wonder why the area under a curve is so important. And remember, when we are accumulating, it's not always just area. We can interpret that to accumulating all the rates of change, which would be the total whatever it is, okay? So if the x-axis is measured in x units and the y-axis is measured in y units, then the area of under the curve is measured in x times y. So sometimes the labels, typically you guys are doing pretty well with those, but you'll need to have the correct label if it's an application problem, okay? So I did this on the trapezoid rule, but be careful. If you're given a table of values, you have to use the intervals that they have created. And so that especially becomes important on that trapezoid rule. So if the intervals are not equal, you can't use that shortcut formula. You'll have to do them all individually. Okay, so let's go over example 1. It says, over a period of time, we've got vehicles lining up to go over a bridge. So here is our table of information. We want to use LRAM to approximate the number of cars that have lined up in that hour. Okay, so they don't tell us how many to use, so you always want to use as many as you can. I will draw a picture. If you need a picture, you're welcome to, or you can just use the table. So maybe once you see both, you'll understand how to do it. But at time equals 0, we know we're at 20 vehicles per minute, and that's our rate. So remember, this is a derivative. So when we go to integrate, that's why we're finding the total number of vehicles, okay? Because we would multiply minute times vehicles per minute. That's what that box up above stated. At 10, we're at 25. At 25, we're at 45. At 40, we're at 20, and then at 60, 1 hour, we are at 15. Okay, and so when we draw our rectangles, if we're using LRAM, we want to use the left endpoint. And you can get this from a table without drawing the picture. Oops, that's a terrible one, but you get the idea. All right, and so we've got 1, 2, 3, 4, 5 rectangles. And the area of a rectangle, we'll just have to do this by hand since they're not all equal intervals, okay? And that's kind of the drawback of the table. 1, 2, 3, 4, 5. So then on my first one, it's 10 times its height is going to be that 20. And then that is 15 times its height is 25. And then that's 15 apart times its height is 45. And so it's just you knowing what value to use. That's only 5, and its height is 50. And then my last one is 15 apart, and its height is 20. So as long as you know which value you're using for, you don't really need to draw the picture. But you will go ahead and add these up after we multiply. 15 times 25. It's been a while since I've done that. Uh, 300. And so then we would add those all up. The notation, if you want, let me go ahead and leave some spot, would be from 0 to 60 of, we didn't name it, so I'm just going to call it V of t. Because it's approximately, because we're using an approximation. And we're going to add all those up. 1800. Okay. There we go. All right, example 2, same idea. For some reason, the midpoint really throws people off when we're given a table of values, but it's the same idea. He's going out for a 90-minute run. He starts out too fast and then he slows down. You can kind of see that by the speeds. And then use 3 midpoint Riemann sums to approximate the distance that he travels. Because remember, when you integrate our function, we're going to get the total miles because it's miles per hour and in minutes. So, okay, so this one has 2 tricks. One is the midpoint, but the second is our intervals. So if this is in minutes and this is in miles per hour, we need to convert them to the same unit, okay? And that's often something that you've seen. So we're going to keep it as miles per hour. So we'll convert our times to hours. So we know this is going to be 1. This is now 1.5. And we'll just take that time, like 15, and divide it by an hour. So 0.25. 30 is 0.5. So 0.75. And that's right in the middle. So 1.25. Okay, so be careful of the units. This doesn't happen a lot, but it could. And so then the next thing is out of all of this data, we need to have 3 rectangles. So 0.5, 1, 1.25, and 1.5. Okay, you could do this without a picture, but this kind of explains why I'm going to use what I do. So at 0, we're at 11. I always like to just write the numbers there so I don't have to look at the table again. Then we go to 10. Then we're at 10 again. Then we're at 9. And then 7, 6, and then we are at 0. Okay, so I still have to have equal widths. So if I've got 1, 2, 3, 4, 5, 6 partitions, that means my rectangle is going to be, I'll draw it down here, 1, 2, 3. Does that make sense? Okay, and so they wouldn't give you a set of numbers that these weren't going to be equally spaced for using the midpoint. That's the first thing. So the next thing is, since I'm using these 3 values for my first, I need to use the one that's in the middle. So we're going to use the 10. Okay, and I just draw a little. So I've got length times width, length times width, length times width. So we are still 0.5 wide, and my height is 10. And so if you can see that, the only issue is you kind of have to double account for the endpoints. And so that's what students have the hardest time doing without a picture. So my next one is also going to be, and it doesn't matter if these were evenly spaced or not, just so you know. These happen to be evenly spaced, but it would still be that number of values given. So they won't always have the uniform. So I was just set them up as separate rectangles. So this one is also a half wide, just a coincidence. And its height, the one in the middle, is the 9. And then my last one, same thing. That one, its width is also a half. And its height is the one in the middle. So we're using the 6. Okay. So half of 10 is 5. Half of 9. Which gives us 12.5 miles. Okay, in 1 hour. We'll say total approximate because it's not equal. Okay. All right, so on example 3, it says that a swimming pool contains 63,000 gallons of water. And it's too cold, so the pool drains while pumping in warmer water. So we've got this going in and this going out. So it's kind of like the bananas. It says, using LRAM, approximate how many gallons of water are left in the pool at the end of the period. So the idea is number of gallons I always like to write it out in words, is the number that I start with. Then we're going to pump water in, so add the number that we pump in, and then we have to account for how many is being pumped out. Number pumped out. Okay? So number of gallons left, we'll say that. And it's over 12 hours. That's the value they gave us. We're in the right label. So what we start with, so we'll say from 0 to 12 of our function, let's just call it W. So W of T, total water. Well, we start with 63,000. And then plus, well, the amount pumped in, okay? So the amount pumped in, we're going to use the top part. So if we want to use LRAM, I'm going to do, let's try this without. So we're going to use all the values on the left because I wouldn't use that 12. So we've got length times width. So my length from 0 to 2 is 2 times the height is the 300. Plus from 2 to 5, that's 3 wide times its height is the one on the left, 200. And then from 5 to 8, its width is 3 times, we're going to use 300. And then, so 2 to 5, sorry, 0 to 2, 2 to 5, 5 to 8. So then 8 to 10, we get 2, and it's the 400. And then plus from 10 to 12, that's 2 wide, and its height is 200. Okay, so this is all being pumped in. Now we need to take off everything that's being pumped out. So I'm going to go ahead and just put a big parenthesis there. So now we're taking these out. So same thing, we still want to use LRAM. So we've got each of our heights, and we want to use these values. So we're still 2 wide. So it looks like I'm pumping in and kind of taking out almost the same amount. They're very similar. So 2 wide, and then from 2 to 5, that's 3 wide. That's a plus. 3 times 300 plus, I'll put it there, another 3 times 200. And then 2 times 200. And then 2 times 150. Okay. So we get 1,000. And then let's look at what we can eliminate that's the same. So 2 times 300, those are going to cancel out. 3 times 200, 2 times 200. I'm just canceling out the exact same ones, so it's less math for me to do. So that's it. So then I've got plus, I'm really going to have 800 gallons overall, and we're going to take out 300 more because I had this and this. So we get about, what's that, 500, so plus, so 63,500 gallons of water would be left. Okay. So it's definitely using LRAM. Okay. We would have a different answer for RRAM, but this is also an approximation. Okay. All right, so on your problems, I have some set up. Trapezoid rule, because I didn't do one of those. This solving one, you should have an equation, so I left some room for some work. I didn't do one exactly like this, but we've seen solving in other topics. And then I did include, this is a real free response question. I know you can Google the answers, but I want you to try this one because it's talking about some things here. I don't want to give it away what it is, but table and some interpretation, what things mean. So we go back to derivatives and we start mixing some of our information together. So I thought, you know, I think we're okay with the table idea. So let's try a free response as your homework practice. So I just made it the last 4 questions, okay? So go ahead and give these 4 problems a try and see how you do.